Let's see how even-numbered nuclei behave. Different reactions were used, along with different targets. The steps are shown here, and as you can see in this reaction, 4 N steps are obtained. In another reaction, the chain will be, for example, 5N. In this reaction, it will be 3N. By changing not only the mass of the isotope, but also the atomic number of the target, we can figure out what we will obtain when we use even atomic numbers as a target. For example, plutonium-94. Curium is element 96, uranium is element 92, and californium is element 98. You can see what these decays look like. Let's remove what is shown at the top of the graph. This is what the isotopes of element 116 look like. Here is the decay. This is even-even. This is also even-even. This is even-odd. This is also even-odd. This is the 114th element, which is the daughter of all of these. They are also even-even, even-odd, even-even, and even-odd. If we have about a 10% possibility for alpha decay, then we can see how this decay will continue. We see that it continues, and spontaneous fission occurs only after 5 alpha decays. As you can see, there is a rather large variety of these nuclei. Now let's look at the energy spectra of alpha particles. Let's take even-even. Here is the 118th element that resulted from californium. Here it decays and it has an alpha spectrum. Here its daughter product 116 decays, followed by its daughter product 114, which also decays, and then spontaneous fission takes place. But this is the resolution of the detector. Look, it's just one line, a monoline. This would be expected for even-even nuclei, where there is an allowed alpha transition and where the transition occurs from the ground state to the ground state. Let's take another even-even reaction, such as plutonium-244 plus calcium-48. Here is the 116th element, one line. Here is the second line, and here is its resolution. Now let's take the odd ones. It is surprising that for odd nuclei, everything also fits into one line, with a rare exception when some outliers appear, which show that the transition occurs not only in the ground state, but also in an excited state. But they are few. Thereafter, it returns to the expected monoline again. The same thing happens with this odd-numbered reaction. This is the typical situation as we move closer to the magic nucleus, when both even and odd are lined up so that transitions usually go from the ground state to the ground state, because the magic lies in the fact that the number of states in nuclei near the ground state decreases sharply, so the transitions in these states are observed with great suppression. The second point is that if this transition is allowed, then the Geiger-Nettel rule is fulfilled, which, according to Gamov's theory, the decay probability or half-life is uniquely related to the decay energy. These are calculations, and these red points were obtained with calcium-48. The purple points obtained during cold fusion integrates well with the graph. Indeed, the signals behave as alpha particles resulting from alpha decays should behave. And now the most important thing. Let's compare what the theory predicted with the results of the experiment. Here is the calculation of these alpha decays, which was performed according to the method of Sobichevsky, Muzichka, Patik, and others. This is our group of theorists who considered the alpha decay of atomically even-numbered nuclei on the assumption that there is an island of stability, that a colossal effect will be obtained there, and that there will be new shells. This is what the theory predicts, and this is the result of the experiment. You can see that the results are in agreement with the prediction, and moreover, the experimental points lie slightly lower than predicted by the theory, which suggests that, in fact, the effect of stability is 10 times higher than it was assumed by the theory, and this difference between the theory and the actual results, as is visible here, is 5%, or 250 kilo-electron volt. I would like to point out that the theory itself predicts with an accuracy of around 400 electron volt, that the transition from one nucleus to another is reproduced with a decent enough precision. This picture shows the decays of nuclear masses, and the decays are the masses of nuclei in ground states, while taking into account the shells of super-heavy nuclei. And from that point of view, I believe that this graph is an absolute triumph of theory. This prediction was made long before we started this experiment. I think that people didn't believe that this experiment would ever be possible, but it has been done, and it worked out quite well. Now for spontaneous fission. Spontaneous fission is, of course, considered more difficult. Spontaneous fission is a collective process of tunneling through a potential barrier, a fission barrier. Tunneling is much more difficult than alpha decay. But here is what we know. Experiments show that there is a very strict correlation around the number 152, or rather 152 neutrons, where the spontaneous fission period can change by 10 orders of magnitude if we move away from this magic number. This tendency is interrupted when it comes to element 104, and the isotopes of element 104 behave differently. First, there is no growth here. They move to the right, and growth is only observed as we approach 162 neutrons. These are our points that show that as we get closer to 162 neutrons, the half-life increases by approximately 6 orders of magnitude because there is a lower limit for spontaneous fission. If we continue, we will pass the magic number of 162 neutrons. Moving in this direction is associated with a decrease in the fission barrier. Since the shell effect decreases, the amplitude of the shell correction decreases, and there is no liquid drop barrier, and therefore the barrier decreases sharply. As a result, the probability of spontaneous fission increases sharply up to 170 neutrons. But if we go beyond 170 neutrons, then a new shell starts to form, and then the barrier should increase sharply. Indeed, for isotopes of the 112th and 114th elements, we see a sharp increase as we move to the right of the 170 neutron mark towards a larger neutron excess. It's easy to see that the minimum is right here, and this is the critical point. This is the critical zone with the smallest time frame and highest probability for spontaneous fission. All of the long chains that we have discussed, in the end, fall into this zone where they divide spontaneously. Therefore, the initial alpha decays end up in this critical zone. The synthesized nuclei are shown here. This was the predicted island of stability, a small island, as you can see. Thus, a bridge was made with calcium-48 and actinide targets, and it was shown how the system behaves as soon as we approach the island of stability. I repeat once again that we are not in the center of the island, but on the edge. We are already on the edge. We have observed an increase in the period of spontaneous fission, as I have shown, by 5 orders of magnitude.